In this example, we're looking at the graphing method for solving a quadratic inequality. Here's an example of what a quadratic inequality might look like algebraically. What we're going to want to do is to, first of all, in that equation or inequality, to get 0 on one side of it, and as you can see down here, all of these have 0 on one side already. We're then going to graph the quadratic function that results on the other side. We'll find the x-intercepts and then determine where that parabola is above the x-axis or below the x-axis. So we have the graph of we'll say it's a quadratic function in general. And as we know, any quadratic function is going to have a graph that is a parabola. So if we are looking at where is this quadratic function less than 0, essentially we want to know where is y less than 0. And on our graph over here, we can see that the y values are going to be less than 0 in this region here. All these ordered pairs have y values that are less than 0. And when we want to say what is the solution to this inequality, the question that we're asking is where is y less than 0. And so we're going to use an x interval in order to answer that question. So we would say x is equal to 0 is where this interval begins, and at x is equal to 5 is where this interval ends. And at any of these x values from 0 to 5, they're all going to have negative y values in their ordered pairs. So where are the y values of the ordered pairs less than 0? We'll say they start from 0 at x is equal to 0, and then it goes to x is equal to 5. Now, since the inequality is strictly less than 0, not or equals to 0, then that means the endpoints, x is equal to 0, and the endpoint x is equal to 5, these are not going to be included because at x is equal to 0, the y value is equal to 0, but equals to 0 is not an option, and at x is equal to 5, the y value is equal to 0, and we're not allowed to have y equaling to 0. Again, it's strictly less than 0. So in this next, again, we're still essentially asking where is y less than or equal to 0, and in this case we're going to see that starting at x is equal to 0 and going to x is equal to 5, but this time we are going to include those endpoints, and here we're saying where is y greater than 0. And again, because f at x is equal to this quadratic, but f at x is also equal to y, this quadratic is equal to y, and when we say where is the quadratic greater than 0, we're saying where is y greater than 0. All these ordered pairs have y values that are greater than 0. If you look at any of those ordered pairs, the y coordinate is going to be greater than 0. So where is that happening? Well, that's happening at x values that start way out here at negative infinity and going to x values out here, but then again we're skipping this center area. So it's going to be starting from x is equal to negative infinity to x is equal to 0. We skip over this center area, we pick up at 5, and then the x values go all the way out to positive infinity. Now, because we're strictly greater but not equals to, then we're actually not going to include these endpoints because the endpoints are where the y value is equal to 0. And then for this last example, this inequality is basically saying where is y greater than or equal to 0, and we can see on our graph that again these ordered pairs have positive y values, but this time we're actually going to include the endpoints, right? Because at those endpoints the y values are equal to 0, and equaling to 0 is allowed. So we're going to say from the x values that are all the way out to negative infinity to this included endpoint, here the y value is equal to 0, here the y values on the order pairs are greater than 0, and so we're going to then begin from 5 and going out to positive infinity, and we're going to include these endpoints. So let's clean it up with our interval notation. We'll say from negative infinity to 0, this time we're including, and then from 5 to positive infinity like this.